Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we are going to discuss preparation of a drug. Actually drug is dopamine, but we will discuss first the l-DOPA because it is the precursor drug. Okay, you will learn why I am focusing on l-DOPA. So first we will discuss that means about this drug and its application for Parkinson's disease. It's a worldwide very I shall not say famous, it's an unfamous disease. Okay, so today's discussion will cover few points like the basic idea and importance of this molecule, two chemical pathway for the l-DOPA preparation, which is actually administered from outside, for example orally, and use and the fate of l-DOPA in brain. Actually in brain, l-DOPA converted into dopamine, which is the actual drug for this Parkinson's disease. So a lot of chemistry to be learned in this video, so I request you please watch the video completely and until the end. Okay, let's start. So first of all, we need to understand about the molecules. Okay, molecules, what do I mean? L-tyrosine, it is an amino acid. It's better to say alpha amino acid. And by the way, I have uploaded the synthesis of L-tyrosine because it is needed that from where this tyrosine we are getting, and this tyrosine, how we are converting this tyrosine into l-DOPA, and how l-DOPA is converted into dopamine, then I guess the study will be complete. And so a lot of things, and even why L-isomer, everything. So let's go slowly. See, so first we should know that dopamine is the actual medicine, as I told for Parkinson's disease, but dopamine cannot cross the blood-brain barrier, but l-DOPA can do. This is the point you people should focus. That, see, this is the structure of dopamine, and actually it is not asymmetric. It is not chiral. So it is an easy molecule. So if we administer this thing orally or by injection, it will not go to the brain where it is actually needed for the treatment of Parkinson's disease, because this disease is related to nerves, central nervous system. Fine, but we can't administer, but we need to administer for that purpose this drug, that is l-DOPA. Why? Because it is available, it is capable to cross the blood-brain barrier. Okay, now so l-DOPA is the precursor for the drug. Now let's discuss little bit about blood-brain barrier or BBB. It's a very important membrane type of thing which allows specific chemical nutrient to go into the brain. What do I mean? Everything in your blood cannot pass the blood-brain barrier and affect go to your nervous system or brain. Now it has some advantage, some disadvantage also. Let's discuss some advantage. What is the advantage? For example, you have observed many times we get infected by many infection. Many times we get infection for stomach, because what we consume, if it fine for our body, then it's okay. Otherwise some infection problem, this thing happens in our stomach. In our body we get other different kind of infection, skin, those things. But this thing generally, I repeat the word generally, doesn't affect our brain. Okay, that is you may consider this is a protection barrier. This blood-brain barrier is a protection barrier for us. So this is one of the main advantage. By the way, there are certain pathogens, certain chemicals which can cross, so that is a different issue. Now, and by the way, I am not a biologist, so if you think that my explanation is little immature, please excuse me, and I request you, if you have any better explanation, please write in the comment box and share with other people. Now, what is the disadvantage? Disadvantage is curing. Design for medicine to cure disease related to brain is difficult. Okay, so that is the advantage and disadvantage. That's why you can see, although the dopamine is our main primary drug and it is not asymmetric, still we can't use. We need to use l-DOPA. And how l-DOPA is prepared? From tyrosine. So this is the interesting part of this chemistry. Okay, and by the way, I believe it's a difficult thing to design drugs for brain, because Not only you need to think about the target, where it work, it bind, it degrade, what is the side product, but also you need to think about will it pass the blood-brain barrier. So that is another challenge for scientists to develop medicines or molecules which can cross the blood-brain barrier, act as a medicine and cure the disorder in the brain. Okay, so now an interesting question may come. See, as I told, this dopamine has no asymmetry, and we like this normal molecules, means non-asymmetric molecule. Why? Because it is easy to synthesize. We know if you have a chiral enantiomer, for example this one, so if you follow normal synthetic route, what you can expect? You can expect that 50-50 of the isomer you will prepare through normal chemical transformation, and among 50, one is useful, another is not. By the way, I have already uploaded a lecture about peptide racemization and separation. Okay, so better to say peptide separation of two isomers like D and L. Please visit if you want to learn more. For example, as I told, for example, L amino acid is useful for our body, and suppose this 50% is L and this 50% is D. So L thing we separate, but what about the D? Actually D thing undergo racemization into 50% D, 50% L in this way. Actually this is an enzymatic process. Please visit the lecture. I shall provide the link for better understanding. Fine. Now as another question comes, that since dopamine is an asymmetric molecule, can d-DOPA could be administered as a drug? Actually this l-DOPA is administered as a drug. Can we use d-DOPA, means the other stereoisomer of this l-DOPA? Now question. Not, we cannot. Why? See, our body is a chiral pool, you may consider, and it is selective. So that is the advantage and that is the problem also. Okay, why? Because if you consume d-DOPA, first of all it may create toxicity, or otherwise it may not be converted into corresponding dopamine inside the brain, because the responsible enzyme are selective. Okay, so that's why you can't use l-DOPA. But another point, if you think from the industrial point of view, if you don't need to do any chiral separation, any other purification, then cost of the drug is expected to be low, and if the manufacturing or production cost is less, then it is expected the drug will be cheap and people can buy easily, because ultimate burden goes on the people. So that's why this is that disadvantage. But don't worry, scientists are always there to solve the problem. That's why they invented the method for peptide racemization. And by the way, if you want to learn complete thing, for example preparation of tyrosine, then l-DOPA, means tyrosine to l-DOPA I'll discuss today. So if you want to learn about tyrosine, I shall upload a video. Please visit that lecture for your better understanding. Now let's discuss the synthesis, means the mechanism for tyrosine, L-tyrosine to L-DOPA conversion. So two types mechanism we are going to discuss. First, this is tyrosine, and actually I am not right now I am actually starting from the enantiomer such that we can get pure one. Okay, so first of all, if you use acetic anhydride and reflux, what is expected? There are these one OH, one NH2, so they will be acetyl. Let it fine. Now one question may come in your mind, that sir, you are showing the hydroxyl and amine acetylated, why not carboxylic acid? Actually see, if carboxylic acid got acetylated, ultimate product is anhydride, and you are initially using anhydride, so that's a mixed anhydride ultimately you will get, and the driving force is not that much for that process, so it is reluctant to undergo acetylation. Fine. Now, so in next step what can we do? We can take acetyl chloride and AlCl3. This is actually Friedel-Crafts acylation reaction. Now look at the molecule little carefully. This benzene is substituted 1,4 position. For example, if you consider this position is 1, 2, 3, 4. Now we know that phenolic derivative, actually it's a phenolic ester. Okay, means is acetate, means acetic acid ester of phenol derivative. Fine. Phenol has a higher plus R effect. Okay, that's why. And second point, so that's why, and phenol is ortho para orienting this plus R effect. So this is the ortho position and this is, and see, look at the para position is blocked by this group. So it is this, so the acylation is selective at the ortho position. Fine. So we prepared this compound selectively. Now if we do the hydrolysis means the removal of COCH3. One is ester, so this is actually a amide hydrolysis and this is actually a ester hydrolysis. Okay, phenolic ester. Now question is, ultimately after hydrolysis what we got? We got the OH, we got the NH2. Fine, this thing is needed, but we need one hydroxyl here, we didn't get. And from carbonyl to hydroxyl, what is the best process? That is Dechene reaction. Okay, I have already uploaded lecture about Dechene reaction or Dechene oxidation. Please visit if you want to learn more. Generally, we used to focus on aldehyde for Dechene reaction, but remember ketones can also undergo the same reaction. Okay, and the but remember the aldehydes are more reactive because the electrophilicity of this carbonyl carbon as well as the nucleophilic attack, because carbonyl carbon is less electron deficient and because of 2 substitution attack is little difficult, which is governed by the factor named as Bargh-Dunich trajectory. You may visit the lecture I have uploaded. So the question in this case, reagent needed is hydrogen peroxide and alkali, which generates the actual nucleophile, that is hydroperoxide anion. See, remember that hydroperoxide is better nucleophilic compared to hydroxide due to alpha effect. And by the way, I have uploaded a dedicated lecture about Dechene reduction. You may visit for better understanding. And so first of all, it will attack, and after that migration of aryl group to result this phenolic ester. Now always remember that phenolic esters have better migratory aptitude than alkyl group, point number 1, and second, the medium is alkaline. So in the alkaline medium, what happens? This hydroxyl is converted into O minus, so it increases the electron density further such that the migratory aptitude improves further. So that's why this reaction happens, and ultimately it's a phenolic ester is produced, and upon hydrolysis of this phenolic ester got converted into this drug, that is l-DOPA. Okay, so this is our target drug for this purpose, actually pre-drug you may consider. Now another important question, please remember, that is why the orthohydroxyaldehyde or ketone shows better reactivity than the para-hydroxy in Dechene reaction. And this thing you can understand through the structure, actually hydrogen bonding. So orthohydroxyl means this, and if you take carbonyl means aldehyde and ketone both. So what happens? The hydrogen bonding possible, and these hydrogen bonding makes this center more electrophilic, point number 1, and second, after nucleophilic attack here, the negative charge generated on this oxygen, okay, is stabilized through the hydrogen bonding event. And actually for this Dechene oxidation, 2 RDS redetermining state possible. One is nucleophilic attack of this hydroperoxide to the carbonyl, and second is migratory aptitude. So the first step is favored because of this hydrogen bonding. That's why orthohydroxy derivative shows better reactivity than para. So this is the first way to prepare the l-DOPA. Now second method, let's discuss. In this case same, it is also from tyrosine. First of all, it is Bock protected. Remember, Bock protection means it selectively blocks the NH2. So NH Bock, fine. So now after that what happens? Chloroform, sodium hydroxide, aqueous and heat. What is this condition? This is actually Reimer-Tiemann reaction. Okay, the spelling may be wrong, please check by yourself. So this is actually Reimer-Tiemann reaction, and I have already uploaded dedicated lectures on this. Please visit if you want to learn more. So in this reaction, the actual reaction between CHCl3 and aqueous sodium hydroxide results in the preparation of dichlorocarbene as an intermediate, and this is the electrophile. And actually it is a weak electrophile. Okay, so what happens in the reaction condition, which is actually alkaline in nature, because of sodium hydroxide, these abstract the proton from the phenol and convert phenoxide, and that's why when phenol is converted into phenoxide, means O minus, its electron donation capability or to the ring increases. That's why reaction happens. Now, like the similar previous reason, here the para is blocked, so option left ortho. Okay, and second thing, so this thing is generally preferred for sodium hydroxide. So fine, so ortho hydroxybenzaldehyde derivative we got. Fine. In the second step, if what is done, second step is done that in presence of base chloroform, see, previously it was sodium hydroxide, very strong base, that's why it was able to generate this dichlorocarbene intermediate, but in this case it is potassium carbonate, not that much stronger, so it will never generate carbene, so don't get confused. So in this case chloroform is actually solvent. Okay, please remember. Fine, what happens? So K2CO3, what it does, it abstracts this proton. Now let's compare. Previously at the initial stage it was a simple phenol derivative, and right now this is orthohydroxyphenol. So this thing is actually orthohydroxyphenol. Because of the withdrawing capability of this formyl group, the acidity of this phenolic OH increases. Okay, so first that's why this is abstracted by this K2CO3. Further O minus generates, means in this way, and this act as a nucleophile and attacks the benzyl bromide derivative, means it attacks via an SN2 process. I guess it is not visible. So it attacks through a SN2 process and ultimately benzyl ether is produced. Just look at. Fine. Actually this is a protection. Okay, protection of OH. Now why? Because in the next step you are going to see that this is a hydrogen peroxide oxidation. So we know that phenolic compounds are prone to oxidation to corresponding quinones, and I have discussed preparation of quinones previously. Please visit if you want to learn more. So what happens? There is a chance of unexpected oxidation and waste of reagent. And why this waste is so much dominated? See, we have started with a chiral enantiopure. So it's a costly compound. So we need to take our protection as maximum as we can. And second, if in a reaction multiple products are produced, then there is the headache of purification or separation. So that is introduced another cost, and since the molecule is industrially relevant or important, so we need to keep all the thing in mind while learning or designing anything for industry. Fine. So this is the protection. Now see, there is a free aldehyde group, and in this condition actually you may consider this is a type or modification of Deakin oxidation. Okay, so in this case this PHAC actually, when it's PHAC dimer actually act as an activator for this process, and ultimately this aldehyde group oxidizes to the corresponding hydroxyl. And by the way, what happens fate of this carbon? This is actually formic acid ultimately after workup. So fine. So what we got? We actually got the hydroxyl. Everything is same. Now two type, not everything same. Two problems are there. First problem is this Bock protection. Second problem this benzyl protection. So we have to remove these two protection to get the final l-DOPA molecule. How benzyl protection could be done? That is done by palladium hydrogen. Okay, selective for this. And another thing, how Bock could be removed? Selectively by TFA. So after the second step, this is actually TFA, means it's an acidic medium, and since acidic we need to neutralize, and for that one step needed for neutralization to ultimately get this molecule. And remember, amino acid doesn't remain in this free amino CO2H form, they remain in deuterionic form. That's a different thing. So in this way we can get the l-DOPA also. So just if you compare, the previous one is from ketone to Deakin oxidation to hydroxyl, in this case aldehyde to Deakin oxidation to this l-DOPA. Fine. Now, so we have understood the preparation. Now let's see little bit about utilization. By the way, by background or by profession I am not a biologist, but I shall try to explain as much as I can. So if you find my explanation is immature, Please mention a proper explanation in the comment box so such that other can also get the benefit. Fine. So it is actually a neurotransmitter. Okay. So what happens? What actually our plan? First, l-DOPA we take orally, the medicine. Now after that, l-DOPA goes to blood. So when it is in blood, it need to cross the blood-brain barrier to get the brain. Fine. And in brain, l-DOPA goes. So what happens after that? Means inside brain, what is the fate of l-DOPA? So these l-DOPA actually converted into dopamine. And if you look at the difference between l-DOPA and dopamine, the difference is this carboxyl group gone. So actually it's a decarboxylation reaction. And this mechanism is little different compared to traditional. Actually this L-amino acid decarboxylate I shall explain. This is a very interesting topic. I shall explain in another video. Just right now accept that this happens to get the dopamine. Okay. So actually this reaction is in the brain. Please remember, this is in the brain. Fine. And so this is the medicine for Parkinson disease. Now what happens to this dopamine? Dopamine can further modify to other neurotransmitter like, see, this position, there was one hydrogen, this is converted into hydroxyl group. So this is actually a oxidation, and this thing is done by DBH or dopamine beta hydroxylase or dopamine beta monooxygenase. By the way, I know such kind of remembering of such kind of name is difficult. I have some personal opinion for that. You may think about it. First of all, this is the alpha position, this is a beta. So we are getting hydroxylation on beta. So you may think that, okay, dopamine beta hydroxylase, easy. This is a dopamine molecule, hydroxylation happening. So ACE is enzyme. So dopamine beta hydroxylase. In this way you can remember the name easily. Fine. Fine. So in this way we get this, and its name is actually norepinephrine. Okay. After that what happens? In presence of this PNMT or phenyl ethanolamine N-methyl transferase, this is the enzyme. So just look at the molecule enzyme name, N-methyl transferase. So methyl group transfer will happen to the N, and actually this thing ultimately result in NCH2, and this is named as epinephrine. Okay, so this epinephrine and non-epinephrine are adrenaline hormones. Fine. Now since I am a chemist, so if I say, I need to look at the functionalization, so 1,2-hydroxyamine derivative. So how this could be prepared by chemically? Simple, from epoxide plus amine. So we know that nucleophilic opening of epoxide possible, so amine will attack, and ultimately what it will do after workup, this is 1,2-amino alcohol, and I have already uploaded a lecture on this topic, that is epoxide opening. Please visit. It is a biological, what I am showing here. Chemical analog is this one. Fine. So what we have learned, how the l-DOPA inside the brain converted into dopamine, and finally that is converted into other enzymes. Even another chemical reaction which you can see, that is NH2 to NHCH3. So analogous at such type of methylation, that is one of the reaction is Estueller-Clark methylation. You may visit that lecture if you want to know the details. Fine. So we have discussed the utilization. So in conclusion, what we have learned today? We have learned today that using Deakin reduction or Deakin oxidation, L-tyrosine to l-DOPA means l-DOPA conversion is possible through a chemically possible, and it's an important drug for Parkinson's disease. Why? Because the l-DOPA is converted into dopamine, which is a medicine, actual medicine for the Parkinson disease. Now l-DOPA can cross the blood-brain barrier, but dopamine cannot. A simple logic may be the hydrophobicity. I am not sure, but my personal opinion is hydrophobicity. This dopamine is more hydrophobic, so it may not cross, but whereas l-DOPA is not that much hydrophobic, so it can cross. Difference is one carboxyl group. Now finally, please, if you have any better answer, please write in the comment box. Dopamine and its derivatives like norepinephrine, epinephrine are also act as a neurotransmitter. Okay, so this is the end of this discussion. I hope you have liked or enjoyed this lecture. So if you think my videos are good enough, then please like this video and write your opinion in the comment box. And if you think this video is good enough, then share it with your friends. And if you think my channel is providing you a worthy content, then please subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon such that you can get the notification of every single video I upload. And most importantly, thank you everyone for watching. Stay happy, stay blessed. See you in my next video.